the architecture block probe diagram of 8051 microcontroller. Okay, so imagine our robot friend's body is like a magical castle with different rooms, each with a special purpose. So let's explore the castle. The first part is the ALU, and this is the robot's math room. It's where all the counting and thinking happens. The robot goes here when it needs to solve puzzles or do calculations. Now the PSW, which is the program status word, is the robot's mood board. It shows how the robot is feeling after doing math or making decisions. And then we have the special function register and general purpose RAM. These are the robot's special storage closet. It keeps important information here that it needs to remember quickly. Then the ROM, which is the read-only memory. This is the robot's library. It's books with instructions that the robot always follows. Followed by the PC, which is the program counter. This is like the robot's book. It helps the robot remember which page of instruction it's reading. And then we have the DPTR, which is the data pointer. This is the robot's magical pointing stick. It uses this to find things in its big memory castle. Then we have ports 0, 1, 2, and 3. These are like the robot's hand and feet. It uses these to touch and interact with the world outside its castle. Then we have the system timing and system interrupt timers. These are the robot's alarm clocks. They help it know when to do certain tasks or when something needs attention. Then the data buffers and memory control. This is like the robot's waiting room. Information sits there before the robot decides what to do with it. And then the general purpose area and SFR. This is the robot's playroom. It can store all sorts of fun information here and play with it however it likes. So all these special rooms work together to help our robot's friend think, remember, and do amazing things. It's like having a whole magical castle inside its head. Memory and register organization. So imagine our robot friend has a big magical toy box. This toy box has special compartments for all its different toys and memories. So the A051 has separate memory space for code programs and data. Our toy box has two special drawers in its toy box. Our robot has two special drawers in its toy box. One drawer is for its favorite books, that's the code, and the other is for collection of colorful building blocks, that's the data. We will refer here to on-chip memory and external memory as shown in figure 3.4, which is below here, right? The robot has two types of toy boxes. The robot has two types of toy boxes. A small one it carries everywhere on chip memory, and the big one at home, which is the external memory. In an actual implementation, the external memory may in fact be contained with the microcomputer chip. Sometimes the robot's mommy puts the big toys inside the small one using magic. It's like having a tiny house that's bigger on the inside. However, we will use the definition of internal and external memory to be consistent with A051 instructions, which operates on memory. But to keep things simple, we will pretend that the small toy box and the big toy box are always separate. This helps the robot remember which toys go where. The separate memory architecture is referred to as the Harvard architecture, whereas von Neumann architecture defines a system where code and data share common memory. There are two ways to organize toy boxes. In the Harvard way, that's what our robot uses. Stories and books. Stories and building blocks are always separate in separate drawers. And in the von Neumann way, all toys can be mixed together in one big drawer. Our robot prefers to keep things tidy with separate drawers. So this is the memory representation that we have below. Let's talk about internal memory. So the A051 computer chip has a tiny room inside it called the internal memory. Inside this room, there are 256 different boxes where information can be stored. The first 128 boxes numbered 00H to 1FH are really special because they are like the most important furniture in this tiny room. We call these register banks. They are like the bed and the couch. And then we have another set of 8 boxes numbered 20 to 20H to 2FH where we store special things like lights, and they are called bit addressable RAM, which can be turned off on or off. So after the bit addressable RAM boxes, there are another 48 boxes numbered 30 to 7FH where we store all kinds of cool stuff like notes, drawings, and other things that the A05 needs to remember. We call this the general purpose RAM. The last 128 boxes, numbered 80H to FFH, are super special because they store all controls and settings for the A05 computer chip. Let's talk about register banks, which is 00H to 1FH. The 8051 uses 8 general purpose registers R0 through R7. And so inside the 8051's internal memory room, there are 4 sets of furniture. We call them register banks with 8 drawers each, numbered 0 to 7. So there are four such register banks. Selection of register banks can be done through RS1, RS0 bits of PSW. So we give each set of furniture a name like R0, R1, R2, R3, R4, R5, R6, and R7. Like the names of furniture sets are like R0 to R7. The A051 uses 8 special friends called R0 through R3. So imagine you have a toolbox filled with awesome tools. In the A051, these 8 friends R0 to R7 are like special boxes where you keep tiny treasures, into bracket data, to use for your programs. There are 4 of these toolboxes and you can choose which one to use. Think of having 4 toolboxes in your room. One toolbox might have your building blocks, another your drawing tools, another your musical instruments, and the last one your favorite stuffed animals. The 8051 has 4 sets of these 8 registers, so you can pick the one with the data you need right now. RS and R0 are the secret switches that pick the toolbox. These secret switches, RS and R0, are like buttons on your toolbox. Pressing a specific button lets you open the toolbox you want to use. On reset, the default toolbox is number 0. When you first start playing with your tools after a reset, a toolbox number 0 is automatically open and ready for you to use. These special boxes are fun in games like add the treasures. The instructions you write are like fun games. The 8051 plays with its treasures. In the game Add the Treasures, you tell the A051 to take a treasure box from box number 2 R2 and add it to another special box called the accumulator, like a treasure chest filled up. Add a R2 adds the value contained in R2 to the accumulator. This sentence is like the rule for the Add the Treasures game. It tells the A051 to take a treasure box from toolbox number R2 and put it in the accumulator, adding it to whatever treasures are already there. So add a R2. Note, since R2 happens to be memory location 02H in the internal memory, the following instructions has the same effect as the above instruction. So add a 02H. So it's like this part is a bit like a secret shortcut because toolbox number 2 R2 is actually in the same spot into brackets memory location 02H as a space in your main storage area internal. You can also use instruction that just says add the treasure from memory location 02H to the accumulator, and it will have the same effect as the first instruction. So the magical world of the register bank in 8051 microcontroller, where you have specific boxes to store treasures, data, secrets, switches to pick the right boxes, and fun games to play with your treasures. Let's talk about the bit addressable RAM 20H to 2FH. Imagine a special toy box called RAM where we can store tiny building blocks called bits. These bits are like tiny Lego bricks that can be either red 1 or blue 0. The bit addressable RAM is like a tiny section of the toy box where we can play with these bits, and it's located in a special area called 20H to 2FH. It's like a secret compartment where we can store our favorite tiny toys. The 8051 supports a special feature which allows access to bit variables. You know how we can pick up individual toys from the toy box. The 8051 is like a super cool robot that can pick up these tiny bits and play with them too. It has a special power that lets it access these bit variables like a magic wand that makes the bits appear. In all, there are 128 bits numbered 00H to 7FH. Imagine we have 128 tiny toys, each with a special number from 00H to 7FH. That's like having a whole collection of tiny blocks, each with its special name. A bit variable can be set with a command such as set B and cleared with a command such as CLR. So we can use special commands like set B to make a bit red, which is 1, and clear to make it blue, which is 0. It's like using a special spray paint to color our tiny toys. Example, instructions are set B25H, set the bit 25H becomes 1, and clear 25H, clears bit 25H becomes 0. So if we say set B25H, it's like saying make bit 25H red, which is 1. And if we say clear 25H, it's like saying make bit 25H blue, 0. It's like following a recipe to make our tiny toys change color. And note, bit 25H is actually bit bit 25H is actually bit 5 of internal RAM location 24H. So this is like a secret code. The 25H is actually a special name for a tiny toy that lives in a bigger toy box called internal RAM at a special address called 24H. It's like a treasure hunt to find our tiny toys. The bit addressable area of the RAM is just 16 bytes of internal RAM located between 20H and 2FH. So the bit addressable area is like a small shelf in our toy box where we can store 16 special toys and have 8 tiny bits each. It's like a special section of our toy box where we can play with our tiny toys. General purpose RAM 30H to 7FH. So you know how we have special toy boxes for our tiny bits. Well, the general purpose RAM is like a bigger toy box where we can store all sorts of things like toys, blocks, and even tiny notes. It's like a big storage bin where we can keep all our favorite things, and it's located in a special area called 30H to 7FH. These 80 bytes of internal RAM memory are available for general purpose data storage. So we can store up to 80 special things in this box. We can use them for all sorts of things like building a tower or writing a secret message. However, these 80 bytes are used by the system stack and in practice, little space is left for general storage. It looks like our toy box is being used by someone else too. The system stack is like a special helper that uses some of our toy box space to keep track of things. So we might not have as much room as we thought, but that's okay. We can still use it to store some of our favorite things. The general purpose RAM can be accessed using direct or indirect addressing modes. So we can use special ways to get to our toys in the toy box. Direct addressing is like using a special map to find our toy right away, while indirect addressing is like using a treasure hunt clue to find our toy. Both ways work, and it's like solving a fun puzzle to get to our toys. In examples of direct addressing, move A6AH reads content address 6AH to accumulator. Okay, so if we say move A6AH, it's like saying, hey, go get the toy at address 6AH and bring it to me. And it's like our special helper brings us the toy right away. Examples for indirect addressing: use register R0 or R1, move R1 #6AH, move immediate 6AH to R1 move A at R1, move indirect R1 contains address of internal RAM which contains data that is moved to A. We can use special helpers called registers like R1 to store the address of our toy, then use that helper to get our toy. So in order to explain, let's explain move A6AH reads content of address 6AH to accumulator. Imagine you have a toy box with a special address label on it like 6AH. The move A6AH command is like saying, hey, go get the toy from the box with the label 6AH and bring it to my special area, which is the accumulator. Move R1 6 hashtag 6AH, move immediate 6AH to R1. So now we are using a special helper called a register R1. The command move R1 6AH means take the address label 6AH and put it in my helper R1's pockets. Move A, comma, at R1, semicolon, move indirect, column, R1 contains the address of internal RAM, which contains data that is moved to A. So our helper R1 has the address label 6AH in its pocket. The command move A at R1 means, hey helper, use the address label in your pocket to find the toy in the toy box, which is the internal RAM, and bring it to my play area, which is the accumulator. So these two instructions have the same effects. These two instructions have the same effect as the direct instruction above. So using the helper R1 to get the toy is like taking a detour to the toy box, but it's the same as going straight to the toy box with the direct address 6AH. Both ways we get the toy to our play area, which is the accumulator. So let's talk about special function register. The special function registers are located in within the internal memory in the address range 80H to FFH, which I'll show in the figure below. So first of all, firstly, you know how we have a special toy box, which is the internal memory, where we store our favorite things. Well, inside that toy box, there's a special section called the special function registers that help us two important jobs. It's like a tiny toolbox inside our toy box, and it's located in a special area called 80H to FFH. Not all locations within this range are defined. So not all tools in our tiny toolbox have, which is the SFR, have a specified job yet. Some are still waiting to be discovered. Each SFR has a very specific function. Each tool in our tiny toolbox, which is the SFR, has a specific job, like a hammer for building or a screw for fixing things. Now, each SFR has an address within the range 80H to FFH and a name which reflects the purpose of the SFR. So each tool in our tiny toolbox has a specific name and address, like a label on the tool that says what it's for. It's like a special ID card for each tool, right? Although 128 bytes of SFR address space is defined, only 21 SFR registers are defined in the standard 8051. So our tiny toolbox SFR has 128 slots for tools, but only one of them has a special job right now. The rest are waiting to be discovered. Undefined SFR addresses should be accessed, as this might lead to some unpredictable results. So basically, try to use a tool from the toolbox, which is the SFR, that doesn't have a special job yet. It might not work properly and could get confusing. Note that some of the SFR registers are bit addressable. Some of our tools in the tiny toolbox can be used in a special way, like using a tiny screwdriver to fix a small screw. SFRs are accessed like normal internal RAM locations. So we can use our tools from the tiny toolbox SFR in the same way we use our toys from the toy box internal RAM. It's like using our tools and toys together to build something amazing. Okay, so think about this. We are going to discuss it right below here, which is the SFR register layout. First of all, port registers, SFR, which are the port registers. And let's jump into it. So the standard 8051 has four 8-bit I/O ports. Port 0, port 1, port 2, and port 3. So our special toy box 8051 has four special doors called ports. Port 0, port 1, port 2, and port 3. And that help us connect with the outside world. For example, port 1 is a physical 8-bit I/O port on the 8051. So one of those doors, port 0, is a special way for our toy box 8051 to talk to other toys and devices outside. So read input and write output. Access to this port is done in software by accessing the SFRP0 register, which is located at address 80H. We can use special software tools to open and close that door, port 0, by using a special key, SFRP0 register, that's hidden in a special place, address 80A. SFRP0 is also bit addressable. That special key, SFRP0 register, has tiny t into brackets bits that we use to unlock specific parts of the door into brackets port 0. And each bit corresponds to a physical I/O pin on the 8050. Each of those tiny bits match a specific pin on our toy box 8051 that help us connect to the outside world. In example, access to port 0 set B P0.7 semicolon sets the MS bit of port 0. We can use a special command set B to make the biggest two MSB bits of our special key SFR port 0 register stick out, which opens a special part of the door, port 0. CLR P0.7 semicolon clears the MS bit of port 0. We can use another special command clear to make the biggest two MS bits go back in, which closes that special part of the door, port 0. The operand P0.7 uses the dot operator and refers to bit 7 of SFR P0. So when we say P0.7, we are using a special way, into brackets dot operator, to talk about the 7th tooth of our special key. The same bit could be addressed by accessing the bit location 87H. We can use our special address 87H to find the same 7th tooth, bit 7 of our special key. It's like having two ways to find the same special tooth. Thus, the following two instructions have the same meaning: CLR P0.7, CLR H7H. Let's try again to reassess this. So, example, access port 0. Example, access port 0 sets BP0.7 sets the MS bit of port 0. So think of set B like a command to set a bit. To set a bit B into brackets 1, P0.7 refers to bit 7 of port 0, which is the 7th tooth on our special key. So set B P0.7 means set bit 7 of port 0 to 1, like sticking out the 7th tooth. And CLR P0.7 clears the MS bits of port 0. So what happens is clear is like a command to clear a bit, set it to 0. Again, P0.7 refers to bit 7 of port 0. So clear P0.7 means clear bit 7 of port 0, like hiding the 7th tooth, right, of port 0. These commands help us control individual parts bits of port 0, which correspond to physical pins on the microcontroller. By setting or clearing these bits, we can interact with external devices connected to those pins. Let's talk about program status word. Program status word is used to indicate the arithmetic condition of accumulator. So you know how sometimes we do math problems and get an answer. Well, program status word is like a special report card that shows how the math problem went. It tells us everything added up correctly or if there were any issues. The program status word register is an 8-bit register. So the report card has 8 little boxes with bracket bits that helps us understand the math problem. It's like a tiny piece of paper that can hold 8 small notes. Okay, it is also referred to as the flag register. Some people also like to call this report card, which is PSW, the flag register. It's like a special name for a special paper that helps us know how our math problems are going. Although the PSW register is 8 bits wide, only 6 of its bits are used by the 8051. So our report card has 8 boxes, but only 6 of them are actually used by the 8051. It's like having a few extra spaces on our report card that we can use for other things, right? And now the two unused bits are user definable flags. So what is happening here is that these two extra spaces into brackets bits on our report card, the PSW, can be used for anything we like. It's like having two special stickers that we can use to make our report card, to mark our report card with a big A plus or smiley face. Okay, so now the four of the flags are called conditional flags, meaning they indicate some conditions that result after an instruction is executed. So 4 of these boxes into brackets bits on our report card tell us about special conditions that happen when we do math problems. It's like a gold star on our report card for doing a great job. These 4 are carry, CY, auxiliary AC, parity P, and overflow OV. So those 4 special conditions are like special stamps on our report card. Carry means we had to carry a number over to the next box. Auxiliary means we had a special kind of carry. Parity means we checked if our answer was odd or even. And overflow means our answer was too big for the box. The bits PSW.3 and PSW.4 are designated RSO and RSI respectively and are used to change the bank registers. 2 of those boxes into brackets bits on our report card, the PSW, have special jobs. They help us switch between different groups of boxes into brackets registers so we can do more math problems. The PSW5 and PSW1 are general purpose status flag bits and can be used by the programmer for any purpose. 2 more boxes into brackets bits on our report card, the PSW, are like special wildcards. We can use them for anything we want, like marking a special accomplishment or noting a special problem. The program status word is at address D0H and it's a bit addressable register. So our special report card, the PSW, lives in a special place called the address D0H, and we can look at each box bit individually to see what's going on. It's like having a special map to find our report card. Let's discuss carry flag. So this flag is set whenever there's a carry out from D7 bits. So you know how sometimes we count and we need to carry a number over to the next box. Like when we count blocks and we have too many for one. This special flag called the carry flag gets marked when we need to carry a number over from the biggest box D7. It's like a little reminder that we have too many blocks. This flag is affected after an 8-bit addition or subtraction. So this carry flag gets changed when we do addition or subtraction with all 8 boxes. It's like a special helper that keeps track of our boxes when we count or take some away, right? It can also be set to 1 or 0 by an instruction such as set B, C, and clear C. But we can also tell this carry flag CY what to do directly, like saying set the flag to 1 into brackets set BC, or clear the flag clear C. It's like giving our special helper a specific task to do. Okay, let's talk about the auxiliary carry flag. If there is a carry flag, if there is a carry from D3 to D4 during an add or sub operation, this bit is set, otherwise it is cleared. So there's another special flag called the auxiliary carry, and it's like a helper that watches what happens when we add or subtract numbers. If we need to carry a number from one box D3 to the next D4, this flag gets marked, otherwise it gets cleared, like a little reset button. This flag is used by instructions that perform BCD, binary coded decimal arithmetic. The auxiliary carry flag is special because it helps us do special math problems called BCD arithmetic, and it's like a secret tool that only works for a certain math problem, for certain math problems. Parity flag. The parity flag reflects the number of ones in the A accumulator register only. There's another cool flag called parity. It's like a counter that checks how many 1 blocks we have in our special A register. It only looks at that one box like a special spotlight. Okay, and if A register contains an odd number of i's, then P is equal to 1. Therefore, P is equal to 0 if A has an even number of i's. Okay, so if our special box A register has an odd number of ones of 1 blocks, the parity flag P gets marked with a 1. But if it has an even number of 1 blocks, the flag gets cleared to 0. It's like a little game for odd and even. Let's talk about the overflow flag OV. This flag is set whenever the result of a signed number is too large, causing the high order bit to overflow into the signed bit. Okay, so you know how sometimes we do math and the answers get too big for our box. Like when we count blocks and we need a bigger box. The overflow flag gets marked when our answer is too big and spills over into the special sign box. It's like a warning that our box is too small. In general, the carry flag is used to detect errors in unsigned arithmetic operations. So we have another flag called the carry CY that helps us find mistakes in our math problem that don't have signs like plus or minus. It's like a special helper that checks our work. The overflow flag is only used to detect errors in signed arithmetic operations, but the overflow flag is special because it only helps us find mistakes in math problems that do have signs like plus or minus. It's like a secret tool that only works for certain math problems.